Hi, we are now going to talk a little bit on some special type of models that are using matrices, right? If you remember, a matrix is here. We're gonna discuss a type of models that involve arrays. This is an array of numbers, okay? Or you can also think of this as a table of numbers. So usually, in general, we say that matrices are rectangular, right? And we refer to this this dimension of the matrix as a row, and then the matrix is a two-dimensional array. There are columns. We go along those other dimensions, right? So there is a whole branch of mathematics which develops theory. In fact, it's called matrix theory. You may also remember this if you look back and refresh your memory on about the good old days of linear algebra. Okay, linear algebra. Linear algebra is the type of algebra we learn to deal. Sometimes the motivation for linear algebra is to solve linear systems of equations. That's the starting point. There are other ways of learning linear algebra, and certainly significant portion of that branch of mathematics deals with the theory of these objects, which we call matrices. Today, we're going to see them, right now, we're going to see them in action, and we're going to see them in use for mathematical models of population. So again, we are so far, we have been writing things like dx1 dt, okay? And then we write an expression, for example, on dx2 dt and dx3 dt and so on. So we've been writing derivatives of, and when we have those types of models, here x1 really means x1 of t. x1 is a function of t, and typically we say that this denotes size. It may also denote density, volume, or some kind of quantity that is quantifiable and measurable, but is we can take measurements on time. This is a time-dependent quantity, okay? So another way of keeping track of the time evolution is defining, for example, x1 still as, with the previous notation, when we're using a derivative, we usually assume that t, the time variable, is a continuous variable. Another way of keeping track of population size or volume or density is by, instead of taking continuous steps, or by taking steps within a continuous interval, we can define those only on discrete time steps. So we can say something like this: x1 at 0, x1 at 1, x1 at 2, x1 at 3, all the way to, sorry, this is supposed to be x1 at, I don't know, 1000 or something like that. So you see how here the argument is this quantity that we specify, and is exactly a discrete. It's not quantity that comes out of a continuous interval. It's a discrete, in this case, an integer, positive integer number. So these are time steps. This is the other representation in which we could represent population size or population volume by only counting discrete time steps, okay? Again, for where we're going to see here in these next few slides, we're going to use the notation x here in bold as a notation for a vector that stores sizes. I'm here being a little vague here and calling these groups. Okay, these groups may denote maybe there is a way of splitting. We had already seen previously how when you think in terms of basic frameworks for infectious disease or communicable diseases, you think of the compartments. The compartments are defined by some status according to the epidemiology, right? So those can be the so-called groups. But there could be other types of groups. You could segregate or separate individuals according to their height, their size, their age, their gender, all sorts of things, right? So in general, we're here describing a situation where there are two groups. And don't worry too much about this notation here. This means transpose. So this means that this vector here really means x is x1, x2. Okay, so it is a column vector instead of a row vector. So suppose that we're gonna revisit this example. So suppose we have two population sizes we're interested in. Suppose that x0, this means that we know x1 at 0 and x2 at 0, okay? What is that? What does it mean that this is known? Well, maybe we have that x1 is 100 and the other one is 5 or something like that. So when we say that suppose this is known, suppose there are values that we are aware of what are the values of population size at time step 0. That's what we mean. So here is where comes the interesting part. So the interesting part is that now the mathematical model, instead of writing something like dx dt, okay, we're not going to write that. We will write an expression, a formula for the size at step n plus 1. And what is going to appear here on the right hand side is going to be an expression of the size at time step n. So we're going to say that the expression at the next time step is going to be in general, as a nonlinear function, but in this case, it's going to be a function that looks like a times x of n. In this case, it's going to be linear, okay? But in general, we say that f is a map or a function of the state of the system at the previous time step. So this is the future, and this is the present, okay? So at step n plus 1, there will be an evaluation of the state of the system at step n. Okay, so let's look at this in more detail. So at n plus 1, we have that we have this matrix. This is a matrix with two rows. This is a 2 by 2 matrix, and we're assuming that this here is a 2 by 1 vector, which means that the state of the system is also a vector that is 2 by 1. And certainly this means that we multiply this matrix times the values of x1 and x2 evaluated at time step n, okay? So this is an example of a very simple matrix model, a model for population that is defined in terms of a matrix vector multiplication, okay? And the fact that this is written instead of differential equations is written as a recursive formula. Sometimes this is called a difference equation. Instead of differential, it's called difference equation, okay? It's also a recursive formula. You need to know the previous step so you can compute the current step. You need to know the current step so you can compute the step, the next step, right? So if you know the initial value, then here's the other phrase here, iteration. You can carry out an iteration of this system, okay? And so that brings, that motivates the next example. Suppose that we assume here we have initial values equal to 1. Suppose that, what does this mean? This means that x1 at 0 and x2 at 0, they are equal to 1, 1. This is an assumption. We're making this assumption, right? So suppose this is known, and that means we are going to iterate. So what happens when we iterate this system? What does it mean to iterate? Well, it means that if this is x at time 0, then x at time 1 would be this matrix times, maybe write that here. So x kind of, let me write it here. X at time 1 would be this matrix times x at time 0. Okay, that matrix is 3, 1, 0.7, 0, and x at time 0 is 1, 1. Okay, and that would give us, remember how you multiply matrices, right? You can, one way of multiplying matrices is you say this row times that column, so that gives you 3 times 1 plus 1 times 1, and then you have this row times that column, which gives you 0.7. So that means that x, this is giving us that x1 at time 1 is 4 and x2 at time 1 is 0.7. Okay, so now we started with a known value of the population size at time 0, and now we have computed, or we can compute this, the value of the population size at time 1. And once we have this vector 4.7, we can multiply the matrix times that vector, and then we can obtain the population size at the next time step. So let's see, this is how these values here come. This is how these values are calculated, right? So you can see here how this value, you can see how in this row, first in the first column, we're listing what is the iteration number or the time step, right? So at n equals 1, the state of the system is there are 4 in group 1 and there are 0.7 in group 2. And the next row is telling us the state of the system at time step 2. And how are those numbers computed? Well, you basically keep repeating. Iteration is another word for repetition or loop, right? So you keep repeating this operation, which means you're going to take the matrix, which has 3, 1, 0.7, and 0, and now you're going to multiply that matrix by the vector with the sizes on the previous time step. So here you have 4 and 0.7. Right? So this is, again, you take this row times that column, that gives you 12 plus 0.7, and this gives you 4 times 0.7 plus 0. Okay, so that gives you 12.7, and in the second entry you have 2.8. And if you want to move on to iteration, state of the system at time step 3, then what you do is that you take the matrix and multiply the matrix by the population size at the previous time step. That would be 12.7 here and 2.8. Okay, this matrix never changes. This matrix is always the same matrix, right? And this is going to give you these values: 4.9, 8.89. For the next time step, you take this matrix, multiply that matrix times this vector, and that's how these values are computed, and so on. Okay, so this is one way of displaying the values of x1 and x2 as we are evaluating, as we are iterating this matrix model. Okay, so this is our first example of a matrix model. But you can see what can we observe here. Well, you can observe how these population sizes start very. 1 is 1 times 10 to the 0, right? So the order of magnitude here is 10 to the 0. And take a look at x1, for example. So it starts with 1 and 4, and basically in 2 steps there, this 12.7 is basically 1.27 times 10 to the 1. Okay, so this starts with order 10 to the 0, and in 2 steps it increases 1 order of magnitude to 10 to the 1. Then what happens in basically another 2 steps, this is now looking like 10, having order of magnitude 10 to the 2, and quite rapidly there, this now has order 10 to the 3. So you see that in a few steps, the orders of magnitude start increasing, okay? That's a footprint. And you can notice a similar pattern for x2, okay? And I'll comment more on that. Well, may I tell you right now? It seems that quite rapidly, the values of x1 and x2 are increasing very, very rapidly. Are taking jumps in orders of magnitude, right? It goes from tens to the hundreds to the thousands pretty soon with a few more iterations. So this is also very simple to code, right? In R, what you need is a for. You're gonna need a for loop, and you code this up. You also are going to need to have vector matrix multiplication. You may want to review that from our the week when we had that tutorial in R. Basically, you need to define a matrix that contains these values, and then you need to use the operation percentage multiplication percentage, and then you multiply by whatever the quantity is you want to multiply. Okay, so those would be the basic operations. Now, let's visit another example. This is another example of matrix model. Now, instead of 2 groups, there are 3 groups. Here we have that matrix, the matrix of constants in the matrix model, right? And here we have we assume some known initial conditions, okay? And what happens when this model is iterated? Okay, so here we have a different picture. Well, these are different dimensions. There are 3 groups, different values, obviously, of the matrix. But this is the same idea. So you start at step 0. This is the value, this is the state of the system. And to compute this state as step 1, you would multiply this matrix times this vector, and that gives you this vector with those 3 entries. This here, and this over there. Okay, then you take that vector and multiply that vector times this matrix, and then that would give you the state of the system at step number 2, and so on. That's how each of these quantities is obtained. But take a look at the first column here. What's happening to the size of group number 1? That size started with 1. Remember, 1 is 1 times 10 to the 0. 10 to the 0. I was saying 1 is 1 times 10 to the 0. Okay? So it bounces, it goes up to order 10 to the 1, but then it quickly comes down to going from 10 to the 1 to 10 to the minus 2. That's a drop of 3 orders of magnitude. Then it drops 1 order, then it goes back, then it drops again, and by time step number 5, in fact, not only group x1, but you can see here orders of magnitude 10 to the minus 5, 10 to the minus 3, 10 to the minus 5. So what's happening to each of these sizes, of every group, is that in just a few steps, these quantities are rapidly. The fact that they all have powers 10 to the minus something, 10 to the minus 5, 10 to the minus 3, 10 to the minus 5, 10 to the minus 6, 10 to the minus 7, minus 8, minus 5, minus 8, minus 8, minus 7. The fact that is 10 to a negative exponent, that denotes these quantities are all going to 0. They are approaching. They all approach 0. Okay, so they are shrinking. Unlike in the previous example, they were going to orders of magnitude that were 10 raised to a positive exponent. Here, in the previous example, they seem to be growing exponentially, right, to powers of 10. Here, they are still converging to powers of 10, but these powers of 10 are extremely small, and gives us the sense that they are approaching 0. Not the same speed necessarily, but they're all approaching 0. So part of what we are going to discuss now is a feature. The key with these matrix models is to know properties of these matrix. Okay? So what are some important properties? We will see that in just a couple of slides. And let's repeat this iteration, this evaluation. Okay, so we assume we have the model written this in this form, in general form. We let A, so here A is maybe M by M, it's a square matrix with M rows and M columns. We assume the initial condition here, x0, is an M vector. And then when we, when we want to compute the state of the system at step 1, what we do is what we were doing before. We multiply the matrix times the initial condition. In other words, this is A times x0 bar. Then we're going to compute x2, and x2 will be A times x1, right? According to this rule, A2 is A times x1. So, but it so happens that x1 is A times the initial condition. So here we have A times this portion here is x1, and x1 is A times the initial condition. That means that we have here A squared. Now, we're writing there A squared, meaning A times A. You have to remember that matrix multiplication is an operation, right? Well-defined operation in the space of matrices. So when we write something like A squared, or when we write something like A to the 3, here we mean A times A times A. You have to take that matrix, which we're assuming is square, and you have to multiply that square matrix by itself 3 times. There are rules for matrix multiplications. And so this power of the matrix is not like raising, it's not like when the matrix is 1 by 1. When the matrix is 1 by 1, we don't call it a matrix, we call it a scalar. We're talking about either a real number, a complex number, an integer number. And when a matrix is 1 by 1, which is an array of only one entry, then the powers are trivial. You just raise to the power, as we do with numbers. With matrices, raising to a power, not the same thing. We have to multiply the matrix by itself a number of times, okay? And that is what's going on here. So what happens with x3? x3 is, remember, x3 is A times x2, right? And this portion here is x, state of the system at time step 2, that is A squared times initial condition. And so there you have A times A squared is A cube, okay? But this is not raising to a power all entries of the matrix. You have to, this means that you have to multiply that matrix by itself 3 times, okay? So, and you can continue doing this and find, using mathematical induction, it's not difficult to find a pattern that reduces to this formula. This formula tells us the state of the system at time n. We started with this, which is the analogy to a differential equation. That is the model that tells us how to evaluate the model, and we can tell the future based on the present, okay? N plus 1 is the future, n is the present. This here is called the solution. It's called the solution of that model, okay? This is the exact solution. All you need to know here is the initial conditions, and you need to know the matrix A, and then you can multiply that matrix by itself. If you want the state of the system at time step n, then you multiply A times self n times, okay? This is A to the n, means A times A times A, all the way. Here you have A multiplying itself n times, okay? So then the note the remark I'd like to make is that in this type of matrix models, there are certain properties of the matrix A that will come into play, okay? In particular, there is a linear algebra result for calculating powers of a matrix, which is what we invoke next. And like many things in mathematics, you need hypotheses or assumptions. So suppose this matrix is squared and is diagonalizable. Well, diagonalizable. Well, that is another way of saying suppose that A has linearly independent columns. If the columns of A are linearly independent, then that means here you have A, and that means that you can write A as the multiplication of three matrices. This is a factorization, okay? This is here, this is A, and this here is S, and this here is S inverse. They kind of look like that because A is a square matrix, so it looks like a square. And here what we have is the product of three matrices. The two matrices on the right and left, they're kind of shielding the matrix in the middle. They're squares. In the matrix in the middle, I only wrote a diagonal. So this here is going to be called a diagonal matrix, right? A diagonal matrix, the identity matrix, is a trivial example of a diagonal matrix. This type of matrices only have they have non-zero entries on the locations where the row number and column number are identical. So location 1, 1, 2, 2, 3, 3, 10, 10, 25, 25, all those locations, which are called diagonal entries, are non-zeros. Above those locations, there are zeros. There is 0 here, and then there is another bunch of zeros over there, right? So that matrix in the middle is diagonal, and this type of factorization is called diagonalization of a matrix. So all this stuff is good stuff from linear algebra. And the special thing about this diagonalization is that the entries here stored in this matrix that's in the middle, this matrix stores the eigenvalues. The eigenvalues of the matrix A. The eigenvalues, So the result from linear algebra tells us that basically you can multiply if you want to, if you have the diagonalization of A and you want to compute powers, when you start multiplying A times A, you'll be multiplying this times itself, and you can do that a number of times and you will obtain an expression that looks like this, which still has a shape. There is a square, the S matrix is square, there is a diagonal in the middle, and there is another square matrix, right? Importantly, this diagonal matrix stores the eigenvalues, but stores actually powers of the eigenvalues. So what this result is telling us is that the powers of the matrix A have a factorization in similar shape to the factorization of the original matrix, such that the factorization stores the powers of the eigenvalues on this diagonal matrix. Okay? It's a lot of information here, a lot to remember. But one thing to keep in mind is that in general, the eigenvalues, these quantities lambda sub j, in general, the eigenvalues are complex numbers. In general, they are in the complex plane. That means that lambda, what was the complex plane? Complex plane, another branch of mathematics with complex analysis and complex variables, but all that good jazz, all that good story about complex numbers, you can argue that all that starts with the square root of -1. Square root of -1 is denoted with the symbol I, okay, such that -1 is I squared, and a whole branch of mathematics develops, okay, on the algebra and completeness, compactness, a whole bunch of very important and juicy properties and stuff. But in general, a complex number is going to have, it's called a complex plane. This would be an illustration of the complex plane. It's called the plane because here you have the real axis, here you have the imaginary axis, right? So take, for example, the number, I don't know, take the number 3 plus 1i, okay? So here is the number 3, and you can argue here is number 1, and so this point here is, looks like a vector, this point would be 3 plus 1i, right? That's how complex numbers look like in general. When you say lambda j is a complex number, that means that you can write lambda j as the real part of lambda j plus I, this I being square root of -1, times the imaginary part of that complex number lambda j. Okay, so every complex number, you can think of a complex number as a vector in R2, a vector with two entries. The first entry of that vector is what we call the real part. The second entry of that vector is what we call the imaginary part. Okay, then just like quantities in R2, because there are two components, the important, very important thing is the absolute value of a complex number. Typically, they are not called absolute value of a complex number. They have another name. They're called modulus, okay? But they're measured in distance from the origin. So the absolute value square of the modulus of lambda j would be the real part, the square of the real part plus the square of the imaginary part. Okay, that means that if we take square root on both sides, we obtain that the modulus of lambda j is the square root of the sum of squares, where each of those squares is the real part and the imaginary part respectively, right? And that would be the generalization of what is the modulus of a complex number. That is still measuring. Maybe I can modify this a little bit, right? Yep. So I'm gonna say, consider this number here. I'm gonna call that number lambda j. So this has a component here called real part of lambda j, and here this is the imaginary part of lambda j. So when we talk about this modulus, we're referring, this here is the modulus of lambda j. We're referring to the distance from the origin, from number with imaginary part 0 and real part 0, distance from the origin to that location of that complex number on the complex plane. That is what the modulus is. The modulus is a non-negative real number. Sometimes it's 0, sometimes it's positive, but the modulus, like absolute value, is measured in distance to the origin. Okay, so modulus of a complex number. So let's see. Oops, sorry. Turns out that we can't have a criterion to compute powers of n for n sufficiently large. And here's something that I want you to absorb. Complex number lambda j has, if the complex number has modulus smaller than 1, in other words, if absolute value of lambda j, again, this is absolute value for complex numbers, if that is less than 1, then the powers of lambda j are going to go to 0 when n gets larger and larger and larger. Okay, this is very important. So this is telling us that when the modulus is less than 1, then lambda j to the n goes to 0 when n becomes sufficiently large. Okay, this is easy to picture when lambda j is what we know as a real number. In other words, when lambda j has imaginary part 0, we're all familiar with this kind of thing. But now, this is an extension into 2 dimensions, right? So making a connection on that type of that result to our general matrix model that we were discussing. This is the model that we first introduced here, okay? And we know that that model has this type of solution, and we just found a result. If A has linearly independent columns, then we can write A to the n, right, as S times this diagonal matrix times S inverse times the initial condition. The important thing on bringing this diagonalization here is that according to what this value of n is, and according to the modulus of lambda 1, modulus of lambda 2, modulus of lambda 3, all the way to modulus of lambda m, according to whether or not they're less, each of them is less than 1, suppose that they're all less than 1 in modulus, then what we may find is that as these powers get larger and larger and larger, each of these entries becomes smaller and smaller and smaller, which means that this diagonal matrix would become a 0 matrix. And once you have a matrix of zeros here in the middle, that means that your solutions will be going to 0. Something, well, I don't have anything written up over there yet, but so that's one of the results.